Hello student, welcome to our first lesson where we are going to look at Newton's first law of motion. We start with the introduction. Now, a body can only be set in motion when a force acts on it. For instance, if you have a book that is lying on a horizontal table or a horizontal floor, that book will not move unless it is pushed or pulled. And when you push or you pull, you exert what we call the external force. Now, the effects of force on motion, which were studied in Form 1, are based in Newton's 3 laws of motion. Let us look at examples of Newton's first law in practice. You have a cardboard that is supporting a coin, and that cardboard is placed on a tabler. If the cardboard is suddenly frict, it is observed that the card flies off, but the coin falls in the tabler. This is because the coin tends to maintain its state of rest. It was resting, and therefore it does not want to change that state. That is why it is falling, as shown in this diagram. You have a coin here, then you pull the cardboard, you find that the coin is falling inside the tabler because it wants to retain its state of rest. Then if you have a wooden block that are piled, and then you pull the bottom one, you will find that the others will not be disturbed. In other words, we are saying the other blocks will remain in a pile undisturbed, except that their position is lowered because of the downward pull of gravity, as shown in this diagram. You have the pull on this lower block, but the others are undisturbed. Because again, as you pull this one, these others resist that change and they want to retain their state of rest. Then when you are inside a moving train or a car, and then that car or train stops suddenly, you find that you will be thrown forward. Because when you are inside that moving car, your body is also in motion. And now, when the car stops, your body will continue in that state of motion because it wants to resist the change. Now, for this reason, you find that people or passengers are advised to use safety belts so that they do not hit anything if the car stops suddenly. Then another example is when you are having a cyclist who is cycling the bicycle on a level ground. You always find that the bicycle will continue moving even when the cyclist stops pedaling. Because again, the bicycle will resist change of motion. And that through these examples, we have seen that there is a tendency to resist change. If you are in motion, you want to continue with that motion. If you are in the state of rest, you want to continue resting. There is that tendency of a body to resist change. And that tendency brings up the definition of inertia. And this one is defined as the tendency of a body to remain in its state of rest if it was at rest, or in its state of motion if it was in motion. From there, we can move to Newton's first law, which states that a body remains in its state of rest or of uniform motion in a straight line unless acted upon by an external force. Note the key words here. We have that the body can either be in two states. One, either it is resting or it is in uniform motion. Then it won't change those states unless there is an external force. This Newton's law of motion is also called the law of inertia. From there, we have the definition of a force as applied in Newton's first law of motion. We have seen that a body won't change unless there is an external force. So this force is defined as that which produces motion in a body at rest or which changes its existing state of motion. Then from there we move to the definition of momentum. And we say that the momentum of a body is defined as the product of its mass and velocity. So if we have a body of mass m and velocity v in meters per second, then momentum is given by mass, which must be in kilogram, multiplied by velocity, which is in meters per second. So in formula, we have that P is equals to mv. From here, we can be able to get the SI unit of momentum. Remember, we always get the SI unit by looking at the units that you are multiplying. For instance, here we are multiplying kg with meters per second. Therefore, the SI unit of momentum is the kilogram meter per second. The momentum is a vector quantity. In other words, it has both magnitude and direction. Remember, momentum is being multiplied by velocity, or in other words, momentum is mass times velocity. And velocity has both magnitude and direction, and that gives us that momentum is also a vector quantity. Now, the direction of momentum is the same as that of the velocity of a body. For example, what is the momentum of a racing car of mass 400 kilogram driven at 144 kilometer per hour? If we look at this example, the value of velocity that is given is in kilometer per hour. So we have to convert this so that we can work with SI unit. So that is the first step. We have 144 kilometer per hour. We multiply by 1000 so that we can convert 144 kilometer into meters, and then we convert hour into seconds, which is 60 times 60. Therefore, when you key in, you multiply and then you divide, you get that the velocity will be 40 meters per second. Then the mass is given as 400 kilogram. So we proceed as follows. Momentum is equals to mass times velocity. You substitute the values, that is 400 kilogram times 40, you get that it is 16,000 kilogram meter per second. Note that the SI unit must be correct. That way you're able to get your full marks. Then we look to another example. Find the momentum of a body of mass 100 grams moving at a velocity of 20 meters per second. In this case, the mass is in grams. So first of all, we have to convert this mass into kilogram by dividing with 1000. And when you divide with 1000, you find that you will get 0.100 kilogram. Then after that, you multiply by velocity, which is 20 meters per second. And by multiplying, you get that the momentum is 2 kilogram meter per second. Then part B, you're supposed to get the momentum of an object whose mass is 2.0 kg and it is falling from rest for 10 seconds. First of all here, we need to get the velocity. Remember, what is given is the time and the initial velocity. So we are given u, that is our initial velocity, as 0 meters per second. We are also given the time as 10 seconds, and then gravitational acceleration, which is 10 meters per second squared. So we are supposed to get the velocity. And here, we can use the first Newton's law of equation, or not the first equation of linear motion, where we have v is equals to u plus gt, where v is the final velocity, u is the initial velocity, g is the acceleration due to gravity, and t is the time taken. So when you substitute the values, you have that u is equals to 0, g is 10, and t is 10. When you multiply, you get that the velocity v is 100 meters per second. Now you have the velocity and you have the mass, so you can be able to get the momentum. And the momentum will be given by mass times velocity, which is equals to 2 multiplied by 100. You get that it is 200 kilogram meter per second. Then we move to the third example. We have that a body of mass 40 grams rolls on a frictionless surface with a constant velocity of 0.1 meters per second. You are supposed to work out the momentum of the body. We proceed as follows. Mass is given in grams, therefore we convert it so that we can get it in kilogram. We divide by 1000. By dividing by 1,000, you get 0.04 kilogram. Then the velocity is 0.12 meters per second. So our momentum will be 0.04 multiplied by 0.12. And when you multiply, you get that the momentum is 0.00448 kilogram meter per second. From there, we have the assignment. Again, the assignment is testing what we have just covered. So practice. If you find that you did not comprehend the concept, go back, replay the video, and then come and attempt the assignment. So thank you, and let us meet in our next lesson.